This is FRM Part 1, Book 2, Quantitative Analysis, Chapter 11, Modeling and Forecasting Seasonality. All we're going to do in this chapter is take lots of the material that we discussed back in the previous chapter, trend analysis, and maybe modify it a little bit, maybe add some subtleties to it so we can get a better understanding of what this term seasonality means. For example, let's suppose that we're some kind of a retail store and we sell two items. I mean, this is a standard and a classical economics example. We sell lawnmowers and we sell snow blowers. And let's just for argument's sake say that we sell $100,000 worth of lawnmowers, $100,000 worth of snow blowers pretty much every year. But we know that we don't sell the lawnmowers when it's a snowstorm outside, and we don't sell the snow blowers when it's 120 degrees outside. So what seasonality will allow us to do in our trend analysis, in our trend models, is to determine if there's something unique that happens during the course of the year. Now, of course, with the snowblower and the lawnmower example, I mean, that's an obvious notion. But it's only using these trend models where perhaps we can uncover some seasonality that we might not have thought had existed. Only a few learning objectives in this chapter. So we're going to describe sources of seasonality, and we're going to use regression analysis, which we've been doing now for multiple chapters. And then we're going to do some kind of a forecast, which we've also been doing. Let's go ahead and define seasonality. It's a characteristic of a time series in which the data experiences predictable changes and regular changes that occur every calendar year. Of course, this can be due to weather patterns, holiday patterns, school calendar patterns, and any other kind of a pattern that you can think of that is related to a specific time of the year. Let's make sure you understand the difference between seasonality and cyclicality. Remember, back in our original economics undergraduate days, we learned that there are cycles of economic events that occur over time periods that are not really patterned after a yearly event. And so cyclical events typically are much longer than a calendar year. In fact, we're currently in this economic expansion, at least in the United States, that goes back to the end of the financial crisis that ended sometime in 2009 or maybe even 2010. That's very different from a seasonal effect, which are limited within one calendar year. All right, here's a question that I've already tried to answer. Why study this? Of course, seasonality can have a big effect on investment returns. So we can have businesses that have high sales during some particular seasons and low sales during off-peak seasons. But more importantly, because there might be seasonality in stock trading, there might be buy and sell decisions that are based on short-term trading activity only that might influence total capital gains or total investment returns. So what we try to do is we try to eliminate this seasonality from the time series data so that we can study the effect of other components on that time series. Now, to model seasonality, we're going to use our regular old regression analysis, and we spent some time using dummy variables. Let me just remind you, a dummy variable is not really called a dummy variable because it's not very smart. It's called a dummy variable because it can only take on two values, either a 0 or a 1. And so look at the example I have in that second square point. If we have 4 seasons, we can create 4 dummies so that during season 1, the dummy equals 1 and 0 otherwise. And then for the second season, the dummy 2 will equal 1 if it's in the second season, but 0 if it's not, and so on. And this can be summarized by the series of 1s and 0s to give you an indication that for just that first row is, it's 1 during the first season, then 0, 0, 0 during seasons 2, 3, and 4. Then it's 1 again during the first season and then followed by zeros. And so you do the first season and the second season and the third season and the fourth season. So that's what's in that first blue box with the D1, D2, D3, and D4. And of course, they're all followed by the subscript T. So there's that kind of a general model on the bottom left where we have the summation sign, and we're going to just sum all of those dummy variables. In the above case, they'll sum up to 4. And then instead of using beta as our linear regression parameter, we'll just use gamma in this case. All right, so there's that model repeated, and then we're expanding that out to include the 4 dummy variables. So D1, D2, D3, D4, and then all of those slope coefficients. And so what we're assuming is that those slope coefficients are not the same, right? If they were all the same, then there wouldn't be any seasonality, and so we interpret those as the parameters for seasonal factors. Now, how about if we wanted to work with seasonal dummies that are 1 less than the 4 seasons during the course of the year? Yeah, of course we can do this. We can just leave out season 1, so there we don't have a dummy 1 in there. But that intercept term, that constant term, is the intercept for the omitted season. And then those coefficients for D2 and D3 and D4, they provide us with the seasonal change, whether it's an increase or decrease relative to that omitted season. Now, typically what happens in this trend analysis is that we've got the trend model over there on the left-hand side of the equal sign, call it y sub t, and then we have the linear trend, just like we did in the previous chapter, and then we add the seasonal effect to it. Let's take a look at some examples of calendar effects. There is a holiday variation. It's the notion that there are changes in holiday dates over time. I'm making this video right after the Easter holiday, and so depending on particular spring and weekends and all different sorts of other variables, Easter weekend falls on different weekends throughout the year. And so the timing of these holiday events can affect the behavior of most of these series. So you can have an Easter dummy variable if you want to. How about trading day variation? I mean, this is just really interesting from the simple standpoint that, January has a certain number of days, and February has a certain number of days, and March has a certain number of days. None of those days happen to be the same number. So there are different trading days during the course of each month, during the course of the year, and then, every 4 years we throw another day into February. So you can handle this calendar effect by throwing in a trading day variable so that you can see whether 28 or 29 during a leap year or 30 or 31, whether those trading days are critical in trying to estimate a set of linear parameters for whatever the trend variable is. So the complete model can look something like this. So over on the right-hand side of the equal sign, the model has that regular old trend variable, time variable, and then it's followed by some dummy variables, and then a holiday variable, and then a trading day variable. And you can use this. You can estimate the set of linear parameters using regular old ordinary least squares that we've been doing for several chapters. And notice the holiday variables and the trading day variables, they go from I equals 1 all the way up to V2 or V1, and so those V's could be almost any number, I guess, maybe less than 31. And how about taking this forecast to a period that is H steps ahead of us? So the full model is shown in that first light blue box. We've seen that before. And then at time t plus h, all we're going to do is add an h time element to it, whether it's 1 days or 15 days or 30 days or 1 season or whatever it is, or however we establish those rules. And then what we do is, remember, those slope coefficients are not known in the true model. So in order to use this step ahead forecast, we use the ordinary least squares to get our estimates. Remember, we called them the beta hats back in the previous chapters. Well, these are going to be something different in this sense, but they're going to be estimates as well. Let's go ahead and take a look at an example. Let's suppose we're trying to predict housing starts. And this is in California, and it's during a certain time period. We want to do a trend and a seasonal component. And so the output is given to us by that equation right there in the middle of the page underneath the second second block point. Now, this is defined as the winter season is December, January, and February, and then spring, summer, and fall are designated as those other 3-month periods. Note that during the winter season, December, January, and fall, we ignore that. We ignore that variable, presumably because nobody builds houses in the wintertime, even in California. So what does the model predict for March of 2020? So there's the output, and we just put in some of those variables there. So we have 3 dummies and an intercept. We have the quarterly seasonality and the 3 seasonal dummy variables. That must mean that March of 2020 equals YT plus 11. And so we just do all the inputs there and we get 21.7. And since we're doing this in thousands of dollars, in thousands of units, we got 21,700 housing starts predicted for March of 2020. And that takes us through chapter 11. Next up, we'll talk about some cycles.